Thank you, and thanks to the organizers for letting me having a talk in this workshop. Okay, so let's start with some motivations. So we start with some information about representations of the symmetric group. So we know that the irreducible representations of the symmetric group in n symbols can be labeled in a natural way by all partitions of n. Okay, and so I denote these modules by S lambda. And as we saw in J. Taylor's talk, when we consider one of these irreducible representations associated to a partition lambda of n, and we tensor it with the sign representation, we obtain again an irreducible representation. So it is associated with a partition, and this partition is what I call the conjugate partition of lambda. So J called it the transpose partition. So I denote it by lambda prime, and it's just as Jay explained, it's just reflecting this partition lambda with respect to the diagonal, and so we have another partition, and this is the module so associated to it. Okay, so what happens in the, so this is in characteristic 0, I forgot to tell you, and what happens in the characteristic P, what happens in the modular case. So in the modular case, the simple modules of Sn are now can be now labeled by, not by every partition of n, but by p-regular partitions. So what are p-regular partitions? So p-regular partitions are partitions in which no part is repeated p or more times. So here we have an example. Here are all the partitions of 6, and I checked the ones who are p-regular for p equals 3. So for example, this partition have has the part 2 repeated 3 times, so it's not 3 regular. All right. So these modules actually, so these modules in characteristic 0 are explicit and well defined, and we know the dimensions, we know everything. And in the modular case, is not that clear. So this labeling is not as natural as in the characteristic 0 case. For example, the trivial representation. So d lambda. So this is the trivial representation, and lambda 0 is still the partition n. Okay, but for the sign representation, which is still irreducible, so there exists a partition which label it. And what is this partition? So I have to write n. I divide n by p minus 1. I do Euclidean division, and the partition lambda 1 is the partition q plus 1. So r times, and then only q's. So p minus r minus 1 times. And the Young diagram of this partition looks like that. Like here I have r, and these parts so are of size q plus 1, and here in total I have p minus 1 parts. So as you can see already, this is not natural, because yes, I forgot to tell you. So in the characteristic 0 case, so this is characteristic p. Okay. In characteristic 0, so let's see what's the partition associated to the sign representation. So if I do the tensor product of this module with the sign representation, as I told you, I just have to reflect this diagram with respect to the diagonal. So I obtain the partition of 1s. So since this is the trivial representation, this is the partition associated to the sign representation. So what I wanted to tell you with this is that in the modular case, labeling representation with p-regular partition is not that natural, doesn't work as well as in characteristic 0. Okay, so the next question is then what happens in this case when I tensor with the sign representation? So can it still be just conjugating this partition? So no, it cannot be that. Why? Because I'm starting here with a p-regular partition, and conjugating a partition doesn't always give me a p-regular partition again. For example, here, if I take p equals 3, this one is p regular, and this one is not p regular, because there's one part repeated 3 times. So it cannot be conjugation. And then in 1979, Mullineux defined an involution on p regular partitions, so a map defined on p regular partitions, a bijection, and he conjectured it to be the partition we're looking for here. And actually, it was true. Then in 1997, for Anklechev, they proved this conjecture, and so that we can say that this map, the Mullineux map, is like conjugating, like modular conjugation. Okay, but this map is actually difficult. It's very difficult to define combinatorially, as we're going to see later. So you can see already here that it's not easy to define, because to the partition, so as we said, to the partition n, it associates this partition, which this is not clear why would be that. Okay, so this is a difficult map, and why are we interested in understanding it? So this is because we can obtain, actually, by Clifford theory, we already saw this theorem before in the workshop, we can obtain every representation of the alternating group by restricting all representations of the symmetric group. So how does it work? If I consider the simple module associated to a partition lambda, so first in characteristic 0, and if I restrict it to an, then either it remains irreducible or it splits into 2 simple modules. Okay? And this happens, this depends on the partition lambda. So if it's self-conjugated, what I call self-conjugated, that is a fixed point of conjugation, then the module will split, and in the other case, it will remain irreducible. So for the same reasons, in the modular case, we have the same result, but not with conjugation, but with the Mullineux map. So that's why we're interested in the Mullineux map, because if we know, for example, the fixed points of this map, then we can know which are the modules of Sn which split. So that's why we're interested in this. Okay, so how are we going to study these fixed points? So it turns out that the number of fixed points of the Mullineux map equals the number of self-conjugate partitions without diagonal hook length divisible by p. What are those partitions? So let's see with an example. For short, I am going to call them BG partitions. Okay? So self-conjugate means fixed point of conjugation, of reflecting. And so this partition, for example, is clearly like symmetric with respect to the diagonal, so it's self-conjugate. And if I take p equals 3, we will see that the diagonal hook lengths, so that is the number of nodes in a hook for which the corner node is in the diagonal. So here we have 3 diagonal hooks, and the lengths are 13. Here we have 7 nodes, and here we have 5 nodes. So neither of them is divisible by 3, so that this is a BG partition for p equals 3. This is a partition. So the set of all BG partitions has the same number of fixed points of the Mullineux map. Okay, so for short, I'm going to call the fixed points of the Mullineux map self-Mullineux partitions, and this is BG partitions. And the question is, okay, we want to understand these fixed points. So is there a natural or an explicit bijection between these 2 sets, which we know that have the same number of elements? This would be interesting because this set is so much easier to describe than this one. Okay, so for answering to this, so the answer is yes, and for answering to this question, let's see how the Mullineux map works first. Okay, so as we saw before, so this is a map, an involution defined on p regular partitions, and let's see how it works with an example. So I will take p equals 3, and I will take this partition, which is p regular. No part is repeated 3 or more times, and I will consider its border, southeast border. So these are these nodes, and then I will construct a border which depends on p, on 3. How? So I consider the first 3 nodes on the whole border, and when I've taken 3 nodes, I switch to the next row. And I take the next 3 nodes. That is this 3. Then I switch to the next row, and I take the 3 nodes, and then I switch to the next row, and there's only 1 node, but I consider it 2, and this way I defined a border that depends on P, like a P border, we could call it. And then we are going to associate to this partition what's called a Mullineux symbol. So it's a 2-row array of integers. And how is it defined? Well, the first column, this 10, I'm going to count the number of nodes in the P border. So there are 10 nodes, and the 5 is the height of this Young diagram, or the length of the partition. And then I'm going to take out these nodes, and I have a new partition. And I do the same thing until obtaining the empty partition. So I consider its border, then its 3 border. Here it turns out that the 3 border is equal to the border. And we have 6 nodes. The height is 3. Then we have 2 nodes. The height is 2. And then we have the empty partition, so we stop here. And this is the Mullineux symbol of this partition. And you can see that this process, actually I can do the reverse process. I can start with this symbol, and I can, the key thing is there's a unique p-regular partition with height 2 and 2 nodes. So it's possible to go back in this process. There's only one p-regular partition with height 3 and 6 nodes, and that way I go. So let's start. So I started with a partition lambda. I define its Mullineux symbol. Then I'm going to define the Mullineux map is defined by the Mullineux symbol of the Mullineux of lambda. So I take this symbol, I modify it a little. How do I modify it? So it's just a little operation. I had this symbol. I denote the numbers with these letters, and then the symbol of the partition that I'm looking is this one, where SI is AI minus RI plus 0 or 1 if P divides I or not. Okay? So I have a new symbol. And from this symbol, I construct another partition, as it will obtain a different one, okay, because these symbols are different. So I construct the partition as we saw before. So here, for example, there are in total 6 nodes that I added with height 3, and then I obtain this partition. Okay, so this is the Mullineux map. This is the Mullineux map of this partition, and as you can see, is not that natural as in characteristic 0. In characteristic 0, we only had to reflect things. Here, we have to do a super long combinatorial process, which is like kind of a little random, and this partition is not clearly what's associated to tensoring with the sign representation. Why would it be that? But it works. Okay, so we're interested in the fixed points of this map. So it will be difficult to study, but thanks to knowing that there's the same number of elements than in this set, so we're going to find a way. So for this, I'm going to start with the set that interests us now, so the set of BG partitions, and I'm going to define a new symbol on these partitions. So how does it work? So first, I'm just going to define it on self-conjugate partitions. So this is defined for every partition symmetric to with respect to the diagonal. Let's consider this one, and again P equals 3. And how does it work? I consider again the border of this partition, and then since this is self-conjugate, I'm going to define this process like symmetrically. I'm going to define it on one side, on the upper side of the diagonal, and then I'm going to reflect things. So I will define a new P border in this case, as before. So I take the first 3 nodes of the border, and then the next thing that I would have done before in the irregular partitions would be to switch to the next row and consider the 3 nodes here. But I am not going to do that. If when I switch to the next row, the first node that I see is on the lower side of the diagonal, then I stop there and I don't do it. So here it is on the lower side of the diagonal, so I stop and I reflect these nodes with respect to the diagonal. They're going to be part of the new P border. And then I take them off. Okay, no, yes. So I'm going to define a symbol here. So how? So it also has 2 rows, and in the first row I'm going to count them as before. But in the second row, this is not going to be the height anymore, but this is going to count the number of nodes in the upper part of the diagonal or in the diagonal. So here we have in total 6 nodes and 3 nodes over the diagonal. Okay, so we take them off and we get a new self-conjugate partition. It is still self-conjugate because by definition of the border. And I do the same thing until obtaining the empty partition. So again, 6 and 3. Here we have in total 5 nodes, and there are 3 of them above or on the diagonal. And then we have this partition, and this is the BG symbol of this self-conjugate partition. Okay, so this is a new symbol, and what's surprising is that actually if here I consider a BG partition, so a self-conjugate partition, but the diagonal hook lengths are not divisible by P, so a BG partition, then the symbol that I obtain here is the Mullineux symbol of some self-Mullineux partition. So actually, when I consider BG partitions here I obtain the symbol of a fixed point of the Mullineux map. So as you can imagine, this is how we are going to define our bijection, by starting with the BG partitions and obtaining a fixed point of the Mullineux map. Okay, so let's see how this partition works. So I start with the BG partition. I associated its BG symbol. As we saw, this is the Mullineux symbol of a fixed point of the Mullineux map. So here I construct this partition as we did on the first slides. Okay, so for example, this is not clear. This is not clearly a fixed point of the Mullineux map. You cannot say that just instantly by seeing the partition. And this is the bijection. So we can go the other way around. If I calculate the Mullineux symbol of this irregular partition, I obtain this BG symbol. And so here we saw that there was only one way of doing it, and this works also obviously because I told you that it's a bijection. This works the other way around too. How? If I take a BG symbol, I can reconstruct a BG partition by doing it like the same thing over the diagonal and under the diagonal. Let's see how. So I have a BG symbol, and there's only one self-conjugate partition with these nodes, and here there's only one self-conjugate partition with 3 nodes over the diagonal and 5 nodes in total, and I continue like that, and by definition I have a self-conjugate partition, but not only that. Since this is the symbol of a fixed point of the Mullineux map, these hook lengths are not going to be divisible by P. Okay, so we have the bijection. So what do we have? So self-Mullineux partitions, as we saw at the beginning, label some simple modules of the symmetric group in characteristic P. Okay, those who splits upon restriction to the alternating group. So a difficult set to understand because Mullineux map is difficult, and we saw that there's a bijection with BG partitions, which are easier to recognize. So the ideal thing would be to find a set of partitions containing the BG partitions that could maybe label the simple modules of the symmetric group in characteristic P. So that conjugation, so here conjugation will be, yeah, like tensoring with the sign representation here, so making the Mullineux map here would be conjugation here, which is an easier involution. Okay, and that's all. Thank you.
Here's a prime, but from a combinatorial point of view, P doesn't need to be a prime. It just needs to be an odd integer.
Yes, actually, yes, it works for odd integers.
So do you know what happens for even integers?
No, I don't know. I haven't looked at that yet.